Hello and welcome to this new tutorial and welcome to this new evolution strategy we're about to cover, now the natural evolution strategies. And more specifically, we're going to talk about one of the last evolution strategies of this section, the PEPG, Parameter Exploring Policy Gradients. And you're going to see that now the idea is going to be quite different from what we've seen before. Before we had either the simple evolution strategy where we simply sampled a set of parameter solutions from a normal distribution of a fixed standard deviation sigma, and then we covered the covariance matrix adaptation evolution strategy where we sampled a set of parameter solution, but this time with a varying standard deviation sigma, or more specifically a varying covariance matrix C with that adapted computation of the covariance by taking the mean of the previous generation. And each time, the idea is that we sampled the set of parameter solution from that normal distribution, and inside the set of sampled solution, we took the best solution, the red point, and we updated the mean according to that best solutions. And besides, in that last evolution strategy we've covered, the CMAES, remember that we actually took the 25% best solutions to compute, that adapted covariance matrix. And so here we're going to see a couple of things to change. The first one is that this time, instead of, taking a subset of best solutions, to only keep the best solutions, we're going to keep this time even the worst solutions. And that is because, as the author clearly states, weak solutions contain information about what not to do. That's the classic learn from the mistakes. The weak solutions, the worst solutions, will tell the evolution strategy what direction to avoid in order to find that optimal set of parameters. So that's the first thing that changed. We're not going to take, for example, as before, 25% of the best solutions to sample the next generation. But then the second thing that changed, and which is pretty big, is that this time we're going to use again the classic gradient to update the parameters. The center of the natural evolution strategies is exactly what we see here, the parameter update through the gradient. This right here, nabla of j theta, is the gradient of j theta, where j is an objective function. So you have to know about objective functions. Remember the classic reinforcement learning algorithms where, the objective function is simply the loss error between the predictions and the target, and we use indeed the backpropagation algorithm with stochastic gradient descent to update the weight in the directions that reduce the loss error, and we do this thanks to a gradient update where we have the gradient of the loss over the weight. So here, we're going to have an objective function, except that the objective function is not going to be the loss error. It is going to be what we see here, that is the expected value of the fitness score. So what you see here is an integration, so in continuous space, but you can imagine it in a discrete space, in which case it would be a sum, a simple sum over the sampled solutions. F is of course our same function of which we're trying to find the maximum. Z is simply the 2D coordinates x and y, the 2D vector x and y. And then this is important. This is what we call a probability distribution, which is used, of course, to compute that objective function j of theta, where theta, and that's the last thing you need to understand in that formula, theta in our case, of the simulation, is the couple of parameters mu and sigma, where mu is the two means of the two coordinates of the samples, x and y, and sigma is the standard deviation. And so the parameter update that we're going to do through a gradient step here will be exactly the update of the mean mu and the standard deviation sigma. And it makes sense that we're obtaining these parameters in that direction of the gradient of the objective function with respect to the weights, because indeed this is what we're trying to maximize. That, if you see it as a sum, just because it's easier to see it this way, is actually the weighted sum of the values of the function f over our sampled parameter solutions. We can clearly see that this will indicate if we are in a good set of parameter solution, because the higher this is, the closer we will be to that global maximum. And therefore, when we are updating the parameter theta with that gradient step, well, this will lead to new parameter theta, mu and sigma, for which then j of theta will be even larger, will be increased, because what we want to do is maximize that j of theta. And that's why we call it an objective function. An objective function is basically a function that you're trying to optimize, whether it is to maximize it, as it is the case here for the total sum of the rewards, or minimize, as it is the case for the loss function in a classic RL task when you're trying to minimize the loss error between the predictions and the target. Alright, and so that's going to be the technique used here. We're going to have a gradient step updating the parameters mu and sigma, the same ones as what we had here, with the mean of the sample solutions and the standard deviation of all these blue points, surrounding the mean. Well, that's the same here, but we're not updating the parameters by, getting that subset of the parameter solution with the best fitness scores and then updating the mean and the covariance from the new generation. Well, this time we're doing this gradient step. And so that's why we can use some SGD based optimizers like the momentum SGD or the RMS prop or even our classic atom. And that's why in the code, well, here is the PEPG class by the way, but that's why in the code at the top you will find, well, first the classic structure of the optimizer with that probability density function pi, and mostly you will have these classic, SGD optimizers, the basic SGD, then the momentum SGD optimizer and the atom optimizer, and that's, of course, if you want to use the natural evolution strategies such as the PEPG or the OpenAI evolution strategy. So that's why they were here. They're not only used to train the RNN or the MDN. And so let's go back to our, PEPG. That's actually the last one here. PEPG optimizer, inside which indeed you will find the atom optimizer, right? With the learning rate here, which is exactly that alpha here. When you're doing a gradient step to update the parameters which will lead to the best solution of the objective function, well, you always have this learning rate alpha just in front of the gradient. And that's exactly what you have here, the learning rate of the atom optimizer. And so now that you get the idea, well, then you have some more details about the exact computations of the gradient. Again, they adapt the formulas of the gradient nabla with respect to the parameter theta of the logarithm of that density probability function, which, by the way, I'm seeing is also given in the discrete case in which we have a finite population size of n. That's exactly what I was telling you about. This is the computation of the gradient in the discrete case of having a finite population size of n. So make sure to catch this. And then I was telling you that indeed there are some more adaptations of the computations of the gradient, as we can see here and here, where indeed that's exactly what we have here. These are the gradients with respect to the parameter theta, which in our case, in our simulation case, is exactly mu, the mean, and sigma, the standard deviation. Well, here you have the adapted computations, but we don't have to get into the details of that. You clearly get the intuition of the natural evolution strategies with that classic gradient step to compute the new parameter, which will take us closer to the best solutions, to the global maximum, when then we sample a new set of candidate solutions from that updated probability density function. And so what's good is that the author clearly make the parallel between all these formulas that you see here and the evaluation example, as it is clearly stated here. For the 2D problems, the evaluation, well, Z1 is the x coordinate, Z2 is the y coordinate, mu1 is the mean of the x coordinates, mu2 is the mean of the y coordinates, and sigma 1 and sigma 2 are respectively the standard deviation of x and y. So make sure not to miss that as well in case you want to understand better these formulas. All right, so now that we get the idea, let's see the result. Here is the natural evolution strategy in action, and I think the PEPG, that's as it is, I think what is used here, the PEPG. And so we can see that indeed we have some varying standard deviation, several standard deviations, and indeed it's working really well to find the optimal parameters, to reach that global maximum. So that's once again a powerful evolution strategy. And as the author clearly says, I think he says that just below, well, this algorithm is great like the CMAES. However, the PEPG, as I was telling you, is rather used when the number of model parameters exceed several thousands. However, when we don't have that many parameters, which, let's remind, is the case for our full world model, where the controller is simply a single layer linear model, therefore not having several thousands of parameters, while the CMAES is the most appropriate evolution strategy, and that is why that's the one we use for our full world model. The full world model, I'll show you that in the final race, because of course before we're gonna race, well, I'll show you the full code with everything, and I'll show you especially where we connect the PEPG evolution strategy inside the full world model, and I'll actually show you how to change it, in case you want to use another optimizer for the training, even though you'll understand that training the full world model will actually be quite tricky, but anyway, you'll get the code. And so here it is. That's the PEPG evolution strategy. Again, a huge code. I think it is implemented from scratch. We don't import it from any package, so you have all the details, and again with the same process explained and generalized by the author, with the ask and tell and current param and best param. Here they are: current param method, best param method, return the best set of optimized parameters at each sampling iteration. So basically the same structure of the evolution strategies that is common among all our optimizers. Alright, so now we're gonna finish that section with a final little tutorial. That's to introduce the last evolution strategy which we haven't covered yet, and which is the OpenAI evolution strategy, that one, OpenES. So I'll just say a few words about it, because actually the author doesn't get into too much details of the mathematics behind the OpenES, but I clearly want you to have the idea when to use it and its added value. So let's see that in the next tutorial, and until then, enjoy AI.